All right, everyone. Today we're just going to quickly review the important derivative rules and um, talk about a few things about the derivative that you need to know. So before we do the derivative rules, which will be pretty fast because you probably remember them from last year, I want to remind you how derivatives work and what they are. So from the last lesson, we saw that a derivative is just an instantaneous rate of change at a point. So check this out. This is the e to the x curve. Um, Remember, this is just an exponential with a base of e, and e is approximately 2.718. You can use 3 as an approximation for e a lot of the time. Okay, I know that's a pretty bad approximation, but 3 is close. Okay, but here's what I want to illustrate to you about the e to the x curve and why it is so used in calculus. So check this out. I have this coordinate right here. This coordinate is where the e to the x curve equals 2. So the x coordinate just happens to be 0.693, which is also natural log of 2. So the curve goes through this point. So why is e to the x such an important curve? Because if we look at the curve at this point, the output is 2. But not only that, if we were to zoom way in and try to find the rate of change here and just count it out, you would see that the slope here is also, look, 1, 2 over 1. The slope here is also 2. That's what is so impressive about the e to the x curve. It equals its own rate of change. The output is equal to the slope at that point. So I could do the same thing anywhere. So if I were to do it all the way at, let's do 4. So where's 4? Way up here, which means it will have a slope of 4 if we do this right. So wherever the curve equals 4, so ln 4 comma 4, which is, oh wait, where the y coordinates 4, my bad. So where the y coordinates 4, there it is. Where the curve's output is 4, the slope here should be 4. And if we take a look, we go up 1, 2, 3, 4, and it looks like we're right back where we started. So yeah, e to the x is pretty impressive because its output equals its slope. Similarly, which that gets us to the first shortcut. The derivative of e to the x is e to the x. And we know that from last year. You don't have to do the definition of the derivative. You don't have to do any of that. It's one of those ones you just have to memorize. The derivative of e to the x is e to the x. So the derivative at 4 for the e to the x curve is e to the 4. So if I plugged in, let's say 2, so e to the 2, e to the 2, which is 7.38. So if I were to, let's do a smaller one, e to the, let's just do e to the first, 2.71. So if I plug in 1 to the curve, the output is 2.718, which is what e is, and the slope there is also 2.718. The slope equals the output. Now, the other really important curve then is the inverse of e to the x, which is the natural log of x curve. And similarly, it has a pretty nice rule too for what its derivative equals. And I'm sure you remember from last year, the rate of change of natural log of x is 1 over x. So anywhere I go, if I plug in 1, I know the slope is 1 over 1. So the slope here better be 1, and it is. If I plug in 2, we remember from last year that the slope is 1 over the input, and it would be 1/2, and it is. If you look, it's definitely shallower. The slope at 3 for the natural log curve is 1/3. The slope 4 is 1/4, and that's the really cool thing about natural log. It is the input reciprocal of the input that gives you the slope. And sine x, cosine x, secant x, all of these have shortcuts. So that's where your derivative rule sheet comes in. I will give you another copy of this. We will work to memorize them very quickly this year. You can't use your derivative rule sheet for all that long. So I'll give you the derivative rule sheet on Tuesday this year. And when we come back, we will practice all week on finding derivatives. Okay, enough of that. Let's remember the derivative rules. There are 4 big ones that we need to remember. The first one, the power rule. I have included the videos down below from last year, so I'm not going to go crazy in depth, but let's say we have a function, a number to a power. I'm going to keep it general because we need to start getting better at this. I avoid this type of thing in Calc AB, but in BC, let's do it. This just says x is the variable, n is some numerical value, okay? So n is 3 or 4 or 5 or 6 or 7.1 or whatever. If you have a function of the form x to the nth power, the derivative is, remember how this works, you swing this in front and multiply it by whatever's in front, so n, x, and then you decrease 1 from the power. Okay, that's the general rule for the power rule. More specifically, let's do an actual example of this. Let's do a hard one right off the bat because we did so many of these last year. Let's say I have the fraction 2 over 3 rad x, and I want to find the derivative of this. Last year, I taught you how to rewrite this using this idea, a number times x to a power. So you need to get a number in front. You need to bring x to the top somehow. Right now it's in the bottom, which is bad, and you need to raise it to a power. So right now we can see that x is in the bottom and it's a radical. Radical x is the same as 1/2 power, and since it's in the bottom, we can write it as negative 1/2. 2/3 is the number in front, so keep it just as you see it. 2/3 x to negative 1/2. Now don't be excited, you're not done. Some people are like, oh, I did it. You haven't taken a derivative yet. The derivative, then you need to do the power rule. 1/2 times 2/3 is negative 1/3 because there's a negative x, and you subtract 1 from the power, so this is where you go to negative 3/2 power. That is a fine answer for this class. If it was free response, or if it was multiple choice, they might have this as their answer. Ready? They might have this, 3x to the 3/2, or they might even have this, negative 1 over 3x rad x. Because when you have a bigger numerator than denominator for a fractional power, you can rewrite it as the radical part. Side note, you can write this as x times x to the 1/2. And then you get this. So I'm going to be reminding you of this all year. This goes back to multiple choice practice that I want to be doing. But we will practice power rule. We did a lot last year, so I'm not going to go too much into detail on it. Next one, product rule. You give the product of two functions that are different from each other. You can use the product rule. In fact, it doesn't even have to be different. So watch this one. I'm going to give you the general form. Ready? Let's say you have a function h of x, which is equal to one function f times another function g. Well, the derivative of h is, the product rule says take the derivative of the first, multiply it by the original second, plus derivative of the second times original first. And that's it. That is the generalized rule. If you were looking at a textbook, that's how they would do it. Towards the end of last year too, we did a lot of general types of this stuff because the FRQs like to give you general situations like this. So let's do an actual example though. Let's say we had something like you have a function f equal to 3x cubed times, I don't know, natural log x. This is a product rule. How do you know it's a product rule? Because you have one function times another function. Product of two functions. So last year, I did the whole f1, f2, I did the whole f1, f2 notation. And then I had you take the derivatives of each and then do the cross them up. You can do that, but we're kind of past that now. You should be able to do these in your head, especially when it's this kind of simple. If not, go back and watch the old videos if you really want me to break it down more. But for the sake of time, take the derivative of this one, the first one. So we have 9x squared times the original second plus the derivative of the back one times the original first, 3x cubed. You could leave your answer like this if it was a free response, but multiple choice would probably be simplified like this. Done. So notice I didn't have to do all the work. I didn't have to show all of it. You just got to remember the derivative of one times the original other plus the derivative of the other one times the original first one. Order doesn't really matter here because it's all plus and multiplying. So as long as you don't put the 9x squared and the 1 over x together, you're in good shape. So that's the product rule. Quotient rule is similar with slight difference. Quotient rule says if you have a function that is the quotient of two functions, so f of x divided by g of x, then the derivative of that h of x function is low d high, the low one, times the derivative of the high one minus the high one times the derivative of the low one. Low d high minus high d low, all over the thing people forget, all over the bottom one squared. So low d high minus high d low. Now, to practice the quotient rule, let's do this. Let's say I give you the function sine of x divided by cosine of x. Let's find the derivative. So, rather than do the F1, F2 stuff, I'm just going to remember the rule and do it all in the same move. So low, d high. So the low one is cosine x. D high, the derivative of sine x is cosine x. Derivative of sine x is cosine x. Minus the high one times the derivative of cosine. The derivative of cosine is negative sine x from your derivative rule sheets. All over cosine squared of x, because we square the denominator. And we can simplify this one. Cosine times cosine is cosine squared. Sine times sine is sine squared, and there's two negatives, so it's a positive. All over the bottom squared. Now, don't do a bad mistake and cancel the cosines. You can't do that. Cosine squared plus sine squared, they're attached to each other. They are one term, technically. Can't split them up. Okay, you can't cancel the cosines. If you're confused, why ask me? But you can't do it. So you almost could stop there, except if you know your trig. This is a very important identity in trig called the Pythagorean identity. Sine squared plus cosine squared is 1. And now look, 1 over cosine squared is one of our reciprocal identities for trig. That's the same as secant squared. So that's the best answer for this problem. And notice that sine over cosine, in case you did not notice, is the same as tangent. So what have we just proven? That the derivative of tangent is secant squared, which is on our derivative rule sheet. So that's one that you can actually prove for yourself using the quotient rule. So let me remind you what we just did. I started with sine x divided by cosine x. I did the quotient rule. I used an identity here to get to 1 over cosine squared, and then 1 over cosine is secant. So 1 over cosine squared is secant squared. And it turns out that sine over cosine is tangent, and our derivative rule sheet gives us the shortcut here. Tangent x's derivative is secant squared x. So that's one of the ones. I asked you to do something similar on one of the homeworks with a different trig identity. All right, the last rule is the chain rule. Chain rule. This one pops up a ton. So something like this. If you have a function, h of x, which is the composition of functions. In other words, you have a function plugged into another function. How does the derivative of this work? The derivative of this is the derivative of the outside function, keeping the inside function the same, times the derivative of the inside function. That's the chain rule. This is the one that pops up probably the most. An example would be something like, if I have this function, let's say I have sine of 5x cubed minus 3x. Okay, so I liked you doing this last year. Notice we have this function, 5x cubed minus 3x, inside of the sine function. So I box it. And remember, this box needs to be in your answer. So that if you box it in the original problem, your inside function will appear exactly as you see it in the answer also. So when I take the derivative, you take the derivative of the outside function. The derivative of sine is cosine. Box stays the same. You do not change the box here. People always try to take the derivative of both at the same time. No. The box stays the same, but you multiply by the derivative of the box, which would be 15x squared minus 3. That's the answer. Can't multiply these together because this is the cosine of this times the product, or times the 15x squared minus 3. And then this year we will do a couple double chain rules. So let's just do one more and then call it a day. If you've got a chain rule problem that looks like this, what if we have sine cubed of 3x squared plus 7x? This is actually a double chain rule. First, you may rewrite it as sine of 3x squared plus 7x cubed. Same thing. Remember, when the cubed is here, it means the entire function is being cubed. So check it out. We have this function inside of the sine function. And not only that, we have this entire thing inside of the cubed. So we will practice these throughout the year. But the derivative would be derivative of the outside first. So think of it like we have box cubed we're starting with. The derivative of box cubed is 3. That box stays the same. To the second power times the derivative of this black box. The derivative of the black box is the cosine of, and then you keep that inside box the same, times, and now you get to multiply by the derivative of the red box. So 6x plus 7. Okay. We did a bunch of these on formatives. We'll do a bunch again because the AP test will probably ask you 1 or 2 double chain rules, maybe. I don't really know. Sometimes they do, sometimes they don't. But if you need more practice, you can go watch all the videos from last year. We will be practicing derivatives all week, and then I expect you to be able to do them. So, yeah, those are our 4 rules. You'll have a derivative rule sheet with all of the other rules, and this year you are responsible for all of them. So 2 to the x, arctangent x, you gotta know them all. All right, that's it. Goodbye.